P, Assistant Professor from Department of Electronics and Communication Engineering. Respected dignitaries, faculty members and all research scholars here, welcome back to the afternoon session of Atal FDP program. In morning session, we learned on artificial intelligence in biomedical applications. Now, I take this opportunity with immense pleasure to introduce and welcome today's research person, Honorable Dr. P. Ramesh Kumar sir. Welcome you sir. Dr. Okulapuram Ramesh Kumar sir is currently working as Assistant Professor in Indian Institute of Information Technology, Sri City. He is a senior member in IEEE. He completed his PhD degree from IIT Roorkee. He published more than 20 papers in highly reputed journals like IEEE. He also having several publications in Elsewhere, Springer and other reputed publishers. Sir also authored 2 books published by CRC Press and Springer. His current research interests include time domain numerical methods to approach fast transient characterization techniques, modeling of VLSI on-chip interconnects, graphene-based nano interconnects and through silicon vias. He was awarded as the Young Scientist from the Department of Science and Technology, SCRB from Government of India. Other awards of Sir include IEEE Student Travel Grant and he listed in Marquis Who is Who in the World 2016. We are happy to have you sir. I welcome you sir.
Yeah, so good afternoon to everyone. This is Dr. V. Ramesh Kumar. Right. So basically, my core area of research is VLSI, mixed with signal processing. Right. So many people are talking about the interdisciplinary work. So we need to combine more and more departments, right? But here, I will see VLSI is a separate stream and signal processing is a separate stream. This is also something like an interdiscipline, right? If you are having expertise in VLSI and signal processing, you can do wonders, right? People who are having expertise in VLSI, they are able to design only the circuits, right? They are not having that much of knowledge how the signal is flowing, right? How the electrons are moving, right? So what type of effects we are seeing when the interconnects are very close. So those knowledge you don't have basically. Okay. So that's why I want to put this topic VLSI interconnects in signal processing, right? So that you can do some wonders. Okay. So we'll start in a reverse way. Before explaining my objective, right? I'll try to explain what I'm trying to do at the end of this presentation. So everybody are talking about the papers, right? Everybody talking about the research papers. Everybody talking about the IEEE papers, right? For a faculty, it is something like a dream. Publishing the IEEE paper is a dream. For students, solving the IEEE paper is a great thing, right? So maybe in your final year project, you can take a IEEE paper and you solve it. That can be shown as a BTech project, right? So it is a dream for student as well as the faculty. So just I want to show you something. Right. So this is my profile in Google Scholar. I have several publications, maybe 22 and 25 I didn't count actually, but these are very important. The highest citation goes to one paper that is published in this is not visible actually. Anyway, I will read. It is published in IEEE Transactions on Nanotechnology, right? So having 78 citations. And the second paper is published in IEEE Transactions on Electromagnetic Compatibility, having more than 50 citations, right? Means these many times this paper is cited, okay? So anything more than 10 is a great thing. Any paper having more than So especially in research field, right, if you publish a paper, if you get more than 10 citations, is a great thing. Okay. So definitely these two are best two papers. Okay. So both are based on the interconnect only, on-chip interconnects. So at the end of my presentation, I am very confident that you people can understand by seeing these two papers. You people can understand what I did, how I did, and what results I got. Okay. So that knowledge you will definitely have. Right? So this is my objective of this presentation. So once the objective is defined, I no need to discuss the outline. We will straight away go to the introduction, right? Maybe those who are not having a core knowledge in VLSI, they don't have what is there inside the chip. Okay. So if you open the chip, what components you see, that knowledge you don't have. We will start from that point and then we will discuss step by step. Yeah. So if you open a chip, if you open an integrated circuit, basically you will see only the two things. Only two things you will see. You may see many circuits, billions of circuits you will see, analog circuits you will see, amplifiers you will see, digital circuits you will see, like adders, subtractors, memory you will see, SRAM, DRAM, cache memory, right? Sensors you will see, right? Whatever the circuits you are designing, but I will see only two components. One is the device and the second one is the interconnect. Okay. So only two things I will see. MOSFET and interconnect. Okay. So whatever the circuits we are talking about in your BTech or maybe in any field, whatever the circuits you are discussing, every circuit is designed by the MOSFETs plus interconnects. That's it. Okay. Right. So all the MOSFETs are placed on the semiconductor surface, right? Call it as a substrate. Okay. All the transistors are placed on the substrate and all the interconnectors are placed on the silicon dioxide layer on the top, right? On the top. You assume that. So here we are placing the transistors, right? And on the top you place the interconnects in step by step, right? Something like level 8 to level 10. So level 1 I have shown here, right? So this is at first level. Maybe at second level also, the third level is on the fourth level, 5 level, right? Like that we will tie the interconnects, right? We will try the interconnects. And some other components is also there, but that is also an interconnect that actually connects the transistor and interconnect. Okay, so this is the transistor which is there on the bottom. And this is an interconnect which is there on the top, which connects the interconnect and transistor. That is also a metal, but we will give a different name, right? Call it as a via. Okay, via means which connects the transistor and the interconnect vertically. Okay, so interconnects basically they are flowing in horizontal. So this is vertical, right? That's why we call it as a different name. Call it as a via. Correct? Okay, so as I told you, we have different layers of interconnects. So 6 layers of interconnects I shown here. Starting from 1, 2, 3, 4, 5, 6. Right? 6 layers of interconnects I placed here. Right? And these interconnects are categorized into three parts. right? One is a local interconnect, which is on the initial layers, intermediate or semi-global, in between, and global interconnects on the top. The interconnects running on the top, right? They are global interconnects, right? The interconnects running in the middle, they are intermediate or semi-global. The interconnects running on the bottom, they are local, right? So done. So basically, for what purpose we are using the interconnects? For transmitting the signal from one transistor to another transistor, as well as for distributing the power. Right? We need to give the power to the transistors, VGB and ground. So for that purpose, we are using the interconnects. Right? Yeah. So this is one of the very important graph, right, for VLSI engineers, right, which shows the relative delay between the gate and the interconnect. So we have two components in a chip. We already discussed that. Gate and interconnect. Which one is more dominating? Okay, I need to give the priority. Which one is more dominating? Either we need to discuss about the gate or we need to discuss about the interconnect. So that one we can understand from this graph. Right? Yeah. So we will compare the relative delay. In this graph, we can clearly see that the X cross marking is having relatively more impact. Okay. So that is what I want to say. This is having relatively more impact on the overall delay. So that is goes to the global interconnect without repeaters. Okay. So even with repeaters also, this square-shaped marking is having more impact. Okay. So what I want to say that in a chip, the delay is basically determined by the global interconnect, which we are placing on the top, right? So for me, the interconnects are more significant compared to the transistors, right? Yeah. So what are the challenges you are seeing while designing the interconnect, right? What are the challenges you will see definitely? In general, what challenges you will see? The one challenge is, right, maybe you know what is meant by scaling, everybody know what is meant by scaling, right? So because of the scaling of the interconnect, right, the current density is increasing. In an interconnect, the current density is increasing. So what? So what will happen? That we will discuss later. You keep this point in your mind. Because of the scaling, the current density is increasing, keep on increasing. And the scatterings are also increasing, right? Scatterings means the phenomena of the electron, it collides the surrounding electrons, right? Right? The scattering probability is also increasing because of the scaling, right? The resistivity is also increasing because of the Joule heating, right? It means when the operation of the when circuit temperature is keep on increasing, the resistance is also increasing, and the conductivity is decreasing. Resistivity is increasing means the conductivity is inversely proportional to the resistivity. Obviously, it will decrease, which is not acceptable, right? In this graph, I want to show you, right? The resistivity is increasing, right? When the width of the interconnect is decreasing, right? Everybody know resistivity is a physical constant. If you want to calculate the resistance of any conductor, R is equal to rho L by A you will use, right? Where rho is the resistivity, which is a physical constant. We will consider it as a physical constant. Depending on the L and A value, we will calculate the resistance. But here, what happened? It is not a constant. The resistivity rho is also depending on the width of the interconnect. Okay, right? Which is something new. Okay, this is something new, right? So this is happening because of the increasing the scattering effects of the electron. And the next effect is electromigration. Okay. Right? What is electromigration? We will see. You consider a metal, okay, you consider a metal, you inject the electrons at very high rate, okay, you inject the electrons at very high rate and you collect the electrons at the different side. So left side you are injecting, right side you are collecting the electrons, but at a very high rate. So what will happen? What will happen in this situation, right? The electrons will move at the same time, right? At the same time, you will see what is happening, right? Then atoms are also moving. Okay, atoms are also moving, means some portion of the metal is also moving. Okay, right? It is also moving. So because of that, what will happen? You will have some voids and pillows, right? Voids means you can see clearly. So this part is moving, right? This is actually a metal line, okay? Because you are sending the electrons at very high rate, so what will happen? Some portion of the atoms are also moving and they are appearing here, something like a pill type structure. So if you keep on sending the electrons like this, sometimes what happens, after some time what happens? So this metal line will cut, right? It will cut, it will break. It will act as an open circuit. Okay? So this will act as an open circuit. Entire portion is moving, right? So this is also not acceptable. Okay? But we cannot do. That is the physical property of the material. We cannot do anything. What we can do then? We can decrease the current density. Not possible. Every time we are expecting high speed circuits, right? We are working on Intel Pentium octa-core, hexa-core, right? We are keep on increasing the cores. We are keep on increasing the speed, right? We cannot compromise with the speed. So then, what is the other possibility? We change the material, okay? Right? So this is basically a metal, something like aluminum or copper or silver, right? So all these materials will show this electromigration effect. So then what you do? You try to think about some nano devices, which is having very high current density property. Okay, something like means that things we will try to see in coming slides, right? So what I want to stress that the conventional metals like copper, aluminum, right, silver, so these are not useful in current trend. Okay. So we are also having the thermal issues. Okay, means the interconnects running on the top feels more temperature because the current density is very high. Okay, so what will happen if temperature is more? What will happen? If temperature is more, the resistance is more, such that for every 10 degrees rise in temperature, there is a decrease in the speed of 5%. Okay, so that's why you need a air conditioning room if you want to operate a high performance computers, right? Maybe in your computer labs, you need air conditioning. Otherwise, all the computers will fail. Okay, right? So this is the slide that I'm trying to discuss, that copper is no longer useful, that era is gone. Okay, now we need to think about new type of interconnects like metal nanoids, nanotube interconnects, spin-based interconnects, heat transfer, photonics, optical interconnects, 3D interconnects, right? So this is the area where the VLSI interconnect people work. Okay, so this is the slide where we are actually working. So I am working in this nanotube interconnect, right? So this is my area of research. Some other researchers in my group, they are working in some different type of interconnects. Yeah. So this is the material that we are trying to currently working as a VLSI interconnect. Okay, graphene. Maybe you hear this word graphene, right? Very famous material, right? It is having many applications. One application is VLSI on-chip interconnect. Okay, So this is the atomic structure of graphene. It is look like a honeycomb lattice structure, right? If you see the honeycomb, the structure is look like this one, right? The atomic bonding is each carbon atom, okay? Each carbon atom is surrounded by 3 carbon atoms, 1, 2, 3. So these two are single bond and this is double bond, okay? This is double bond, right? The atomic number of carbon is 6. The electron configuration is 1s2, 2s1, 2px1, 2py1, 2pz1, right? This you already know. In order to make the carbon stable, they need 4 more electrons, okay? They need 4 more electrons in order to make carbon atom stable, okay? So for this carbon atom, 1 electron it will share with this carbon atom, another electron here, another 2 electrons here. So 2 plus 1, 3 plus 1, 4. So now the atom is stable, okay? Now this carbon atom is stable. Like this, each carbon atom is bonded by 3 other carbon atoms nearby 3 other carbon atoms, right? So if you see the periodic table, it is in group 4, carbon is in group 4, right? And the allotrope of carbon is a graphene. There are many other allotropes of carbon like diamond, like graphite. They are also come from the carbon only, but graphene is one type of allotrope which is having a honeycomb lattice structure, right? So by seeing the carbon, what we think that it is a semiconductor because it is in the semiconductor group, okay? Because it is in the semiconductor group, just like silicon, this is also acting as a semiconductor. So that's what we assume. But when you see the characteristics, you will really surprise by seeing the behavior of carbon, by seeing the behavior of graphene, okay? So we will try to see the characteristics. This one, very surprising characteristics. So these characteristics you see, this is conduction band and this is valency band. There is a clear gap between conduction band and valency band, correct? So it is a semiconductor. So this gap is in the order of 1 electron volt, okay? So that's why it is a semiconductor. So general semiconductor materials will show the EK diagram look like this, correct? Whereas for graphene, if you see the EK diagram, it will look like this, right? What it means, the conduction band and valency band, they are touching each other, okay? They are in contact, okay? So they are in contact. What it means, it is a metal, okay? So there is no forbidden band, in fact. The forbidden band is 0, but still they are not overlapping, okay? For metal, this EK will deeply go to the conduction band will deeply go to the valency band, but here it is not going, it is not separating, it is just touching, right? It is just touching. So that's why I will give a different name for graphene. I want to give a different name like semi-metallic. It is a semi-metallic. Means it is not a semiconductor, it is not a metal. It is look like a semi-metallic. Okay. So using this property, what we can do, what wonders we can do, we will see. First we will briefly discuss about the graphene properties. Okay. So their mobility is very high, almost 100 times higher than the silicon. Okay. It is very high, it is 10 power 5. Right? For silicon it is only 10 power 3, right? So that we can get a more drift current we will get. We can also see the conductivity of the graphene. It is 10 power 8. The world's best conductor is silver, right? How much it is? It is 10 power 6. Okay, and it is comparable to copper, but it is only 10 power 6. But graphene, you see, it is 10 power 8, 100 times higher. Okay, you see that the thermal properties, this is very high for graphene, right? 4840. What it means, what this value actually shows that the way it dissipates the heat to the environment. Okay. So it receives the power, it receives the heat from the circuit, and at the same time, at the same rate, it will dissipate the heat to the environment. Okay. So it means you don't catch the heat. Okay. That heat will easily dissipate to the environment, which is a good thing. We will see the strength of the graphene. That it is the strongest material ever measured. Right? The strength is 10 times higher than the structural steel. Compared to the steel, the strength is 10 times higher. And it is also used for optical communications. The absorption rate is only 2.3%, and the light emitting ratio is 97.7%, which is very high level. Okay. So that is all about the graphene. So we confirm that we are going to change the material from copper to graphene, right? That is confirmed. Okay. So how this graphene is used for the interconnect, that we will discuss now. Okay. So we are going step by step. So once what we discuss, what is chip, what components are there inside the chip we discuss, and what is the problem of conventional material we have seen, right? And what are the alternatives we have seen. In many alternatives we choose the graphene, and we discuss the advantages of graphene. Now we are going to use graphene as interconnect. Right? Once it is done, this is also clarified, then we will see how the signal is transmitting inside the graphene and in what areas we can work. Okay, so that we can also publish the paper, you can also do your project, right? So those things we will see, and then we will conclude. Yeah. So graphene, we are not using directly graphene as an interconnect, okay, because it is a two-dimensional material and interconnect is a one-dimensional material, right? So first we will try to convert the graphene either CNT, carbon nanotube, or graphene nanoribbon. Okay. So these are one-dimensional interconnects acting as a on-chip interconnect, right? So this is the graphene. Okay, this is a graphene sheet. So we are talking about a sheet. Okay, so this is a graphene sheet made of carbon atoms. You confine the structure. Okay, you confine the structure in one dimension. It is look like a ribbon. Right? Ribbon means it is having more length. The ribbon is having more length, and the width is very confined. Okay. For example, length is something like 2 meters. The length of the ribbon is 2 meters, and width is something like 10 centimeters. Okay. So 10 centimeters width and 2 meters length. So it is not a two-dimensional. Okay. Compared to the meters and centimeter, it is not a two-dimensional. Can be considered as a one-dimensional. So in the same way, so this is confined. Right. This width is confined, and this length is going like meters. Okay, so this is look like a one-dimensional structure called as a graphene nanoribbon. Why ribbon? It is look like a ribbon. Okay, it is look like a ribbon. The confinement can be done in two types. One is zigzag, and the second one is arm chain. Okay, for many of you, these two structures are same. Okay, you see the structures, this one and this one are same, but they are not same. Okay, they are not same. So this is called a zigzag GNR, and this is called as a arm chain GNR, right? That difference I will explain now. Okay, so that difference I will explain now. If you see the cross-sectional view, right, the cross-section pattern. The cross-section pattern of this ribbon and this ribbon is having the zigzag shape. The ribbon in the cross-sectional part is look like a zigzag. Okay, whereas this cross-section is look like a arm shape, right? Like a shape of this shape, right? This is look like a arm shape, right? You can have a depth here. You can have a depth here. And you can rest your arms here, right? You can sit here and you can rest your arms here. So it is an arm shape.